Hello there. We have here a voltmeter is connected into a circuit with the polarity shown in the figure. The sliding contact is moved to end P of the potentiometer and then to end Q. What are the two readings of the voltmeter? So this is basically practical circuits, specifically dealing with what we call a potentiometer, in which you can adjust the resistance of a resistor, in which the sections or the part the resistors are varied will correspond to a potential divider of the potential difference. Okay, so how do we approach doing this question? It basically the circuit can actually be represented into two different circuits, where you can assume that if the sliding contact is at let's do at P first. So what will be the circuit like? It would be, this is your 3 volts plus minus, and then this one will be your Q, and then P would be here. Okay, this one will be, and this one will be your plus minus voltmeter. That means there's no particular resistance across this part of P. So this is when the sliding contact is at P. What happens is that we have another one, which is when the sliding contact is at Q. So hold on, let me just put the polarities first. This one is 3 volts and the other one is 3 volts. So similarly, you have the 3 volts here, plus minus. But instead, if it is at Q, what happens is our sliding contact will be here, plus minus. And this one is minus and plus. And this would be our resistor. Okay. All right. So we have here our 3 volts. This one is our 3 volts. The question is asking, what is the value of the voltmeter V at when the sliding contact is at P, and what is the value of the V when the sliding contact is at Q? So there are many ways, there are multiple ways of going about this. What I'm going to show you here is basically the step-by-step manual way. Of course, in the actual examination, it will be time constrained, where one question you only have 1 minute and 15 seconds for one question, roughly, approximately. But this is the just to explain to you. If you do it one step by step and you are used to it, you should be able to do it instantly. So what we do is basically is based on Kirchhoff voltage or second law, where it says that in a closed loop circuit, the amount of EMF supply will be equal to the amount of the total amount of EMF supply will be equal to the total amount of potential difference or loss in a closed loop circuit. So what we do is actually we need to define our loops first. So let's say, for example, I label this point or this junction as A, and this one is B, and this one is C, and this one is D, where D will be connected to the negative terminal of this 3 volts. So you have one loop, one complete loop, A, B, C, D, A. So we just have to find out what would be the PD across A, B, C, D, A. Okay, so let's do this one by one. The potential difference across points A and B would be a potential drop. Let's say, for example, we just label it as R or VR. Okay, because this is a resistor, therefore it will be minus, which is a loss, minus VR. And secondly would be BC. So this one is positive to negative, so this one will be minus VP. Okay, What about CD? CD is from short to long. That means you have an increase in potential. So this one is 3 volts. And then from D to A is from short to long, also 3 volts here. So here we can all of this loop will be equals to 0, because the total sum of EMF supplied must be equal to the total sum of potential difference used. So let me just write this down properly. So this one will be equivalent to 0. So here we can see that VR plus VP is actually equivalent to 6 volts. Okay, so this is our first equation. Now let's do for our second equation. Similarly, we label the points first. We have point A, and this A is basically similar. So this one is B, and this one is C. So we don't need to consider the resistor here, because A, B, C, A is just a complete loop. A, B, C, and A. So we label this the points A, B, C, and A. So find out what is the PD across A and B. It will be minus VQ. BC would be from short to long, so it will be plus 3 volts. CA, the last one, will be from short to long as well. This one will be plus 3 volts, and the closed loop will be equals to 0. Therefore, here we know that VQ is equals to VQ is equals to 6 volts. Okay. So how do we find out VQ? So VQ is 6 volts. So D and B are our suspects right now. So we just eliminate A and C. So the idea right now is to determine what is P and what is the PD at P. Now for VQ equals to 6 volts, this one is already done. Now how do we solve with this? VR plus VP is equals to 6 volts. So we need to find out what are the other loops that are possible. So we already looked at the biggest loop, which is A, B, C, D, and A. But in fact, we can go for another smaller loop right here. Okay, where here we can automatically see. Let's look at the loop B, C, D, and B, C, D, and B again. So what is the PD of BC? This one would be minus VP. What is CD? CD is plus 3 volts. What is DB? DB is just 0. So this one is equals to 0. So we know here VP is actually equals to 3 volts. Of course, when VP equals to 3 volts, we know that VR, which is the potential difference or the voltage loss due to the resistance R, is also 3 volts here. So VP is equals to 3 volts. So the answer would be D. So the idea here is to determine which loop we want to use, in order, and then we just apply the Kirchhoff voltage law, which is the total sum. Let me just write this down again. Total EMF must be equal to the total potential difference. So that's what we've been doing, looking at the two possible EMF. Or voltage supply, potential difference supplied, and we've got the potential difference loss due to the resistors as well as the voltmeters. Okay, so hopefully this clears things up.